This conference will now be recorded.
Great. Okay, so good morning, everybody. So today we are going to have a longer session. And what I'd like to do is to discuss maybe first the end of the TD 5 or 6 that we started last time. So this was about mainly Hawkes processes, but as we will see, we will also connect to some of the things that were discussed in the last lecture about metastability. And we're going to do this looking at a very simple model of financial transactions and exchanges, and that's part one. Then I think we will make a break, and then we will go to what was supposed to be TD 7, and that is about some simple model of opinion dynamics, if you want. So this is close again to what has been discussed in the last lecture, and this is called in the literature either the Kirman model or the Moran model. So this is also connected to the homework number 7. And so we will try to do this in detail, and then if there is time, I will give you just the idea of the third part of TD 7/8, which is going back a little bit to statistics and discussing, using idea of Brownian motion to discuss tests about, or what are called goodness of fit tests. So how do you check that assumptions that you make on a given set of data and on their underlying distribution are actually good, or whether you have to discard them. So this is in case we managed to arrive there, but let's say the first two parts are the most important ones today. So let's start with the first one that is in the first TD after the exercise that we discussed last time. And I just wanted to start by recalling something that you saw in the lecture. So this was from the last lecture. And the idea is to recall a little bit this concept of metastability and activated dynamics, because this is what we are going to discuss in more detail later on. So in the last lecture, you were discussing things related to these models of choice, where you have many agents that need to choose between different options. And at a certain point, you introduced some dynamics. So S was one of the possible binary choices of the agent labeled by I. And you were writing something like this. So the choice of the agent I at time t was related to the one of all of the other agents by the following expression. So this was the sign of some external field, which I think was called capital H. Then there was some, let's say, term which was specific and typically randomly distributed and specific for agent I. And then you had an interaction term that I write already in the mean field expression. So that was Jij that I here write as J0 over N. So the normalization comes from the fact that you have all-to-all interactions between the agents. So you have to divide by a factor of N in order for this to be of the same order of magnitude of your external field. And then you have the choice of the agent J at the previous time t-1. And in order to discuss this model, at a certain point, you made the assumption that these different random fields were set equal to 0, and then the model can be discussed in terms of a global mean field-like variable, which you can think of as the magnetization, if you want, in the language of spins, which was just the sum over all of your agents of the corresponding variable at time t. And this quantity satisfies a dynamical equation that is essentially Langevin. So there was dm, so this is a total derivative over dt, was of the following form. So the first term, it was convenient to write it as a derivative of some potential, which depend on the particular value of magnetization that you have at time t. And then there was a noise term, which contains some coefficients. So the coefficient was set to 1 in the lecture, I think, but let me call it capital sigma, divided by n, and then there is the usual white noise term. And so as you see, your dynamics is given by, as usual, you have some noisy fluctuations. And then the first term is what people usually call some gradient descent term. So what you are saying is that you have a dynamics in a given potential, that the dynamics wants to push you downhill at the points which are, or towards the points that are essentially minima for this potential, or in general stationary points where the gradient of the potential is equal to 0. And if you had no noise once you reach a stationary point, as you see the dynamics, this is equal to 0, so your dynamics would become stationary and you just staying there forever. But if you have a little bit of noise, then you can have a more richer dynamics, so you can use the noise to escape from these stationary points, and this is what we are going to see today. So in particular, the shape of the potential in the lecture was, oh, maybe I can draw it here. So if you remember, your potential was looking like the usual potential in Ising-like problems. So this was V beta of M when your field H, capital H in here, is different from 0. It had a shape that was more or less like this, with two minima, one of which is the global minimum in here, and the other one is instead a local minimum, which is suboptimal with respect to the global one. And now what we're going to discuss today is how to interpret this local minimum. So in particular, in our language, this will be a metastable state. So what metastable state means is roughly the following. So if you think about this dynamics and you imagine that you start somewhere within the basin of attraction of this minimum. So let's say that my dynamics starts, no, maybe blue is not a good color, starts somewhere in here, then what you expect your system to do under this dynamics, if the noise is small, then the dominant term will be this gradient term. So this gradient term pushes you towards this point in here where indeed the right-hand side is equal to 0. So you would expect that you have some noisy dynamics that somehow goes down into this landscape, and then it relaxes into this metastable state, and maybe it performs a little bit of fluctuations within the basin of this local minimum because you have the noise. And if you're looking at your system in the limit in which n is exactly equal to infinity, so in general we think at n as being a large parameter, but in the limit in which n is strictly infinity, which is the mean field limit, then that's it. So you would converge into this minimum and you will stay there essentially forever. But if n is finite, if you remember the comments that were made in the last lecture, something more trivial, more or less trivial actually, can happen. Namely, you will have a certain instance of times, which are very rare, where your system, which is confined in this region, uses the noise to escape from this local minimum and to eventually converge to the global minimum of your potential in here. But doing this is very hard with these dynamics if your noise is small, because as you see, so if your noise is small, then typically this is the term that wins. And this term, as I said, pushes you down. So in order to overcome this barrier, so this is what was called B in the lecture, is the difference in potential between, let's say, one of the minima and the local maximum. So to overcome this barrier, you need very large fluctuations of your noise that are typically very rare. So rare means that you have to wait a lot of time to see this process occur. And you can estimate what is the time. So this was given in the lecture as well. So let me call tau the typical timescales for this type of jumps. Then what explicit calculations tell you is that this tau will depend on the parameter that you have in the following way. So it will be exponentially large in the barrier, so what I call B here, or actually to be more intuitive, let me call it dV. So this is the difference in potential between the local minimum and the local maximum. And then in front you have this factor of n, which is nothing but, so it would be a factor of 1 over sigma square, where sigma is the variance of your noise. And now in usual applications, whenever you look at Langevin, what people do is to choose the variance of the noise to be proportional to temperature. So noise is a measure of thermal fluctuations. So this square root is in the usual Langevin formalism is of the order of square root of temperature. So you see that this expression here, you can write it as e to the beta times dV. And this is what people call in the literature the so-called Arrhenius behavior. So it tells you that the time that you need to wait in order to jump this barrier grows exponentially in the barrier itself, but also in the temperature, or in the inverse temperature, or if you want, in the inverse of the variance of your noise. And in here, because you're looking at models that are mean field or fully connected, you have this factor of n, which makes, so when n is large, this makes your jump processes very, very rare, meaning that in the limit when n goes to infinity, these jumps will never occur because tau goes to infinity. But if you have a finite size system, even if fully connected, you do have some finite timescales over which you will see this jump occurring. And these are called activated processes or activated jumps. I hope that you can see. That are something that is studied even currently in situations a little bit more complicated than these, for example, in systems that are glassy or which have very many metastable states. So what we are going to see today with the exercise number 1 is something quite similar. So we will also estimate times for jumps over barriers of a potential. But in this time, so this time, this, let's say, jump time will be also large in the model that we are going to see, but it will be large in a parameter that is not the number of agent, capital N, but which is another parameter that we will call epsilon, or 1 over epsilon, which is related to nonlinearities in your model. So the setting is a little bit different, but this was just to somehow remind you that in essence, the type of processes that we want to describe are exactly of the form of what you saw in the previous lecture. And let's keep in mind this expression, because at the end of the exercise, we will compare with the case of Ising-like potentials. Okay, so having said this, let's go to the exercise, and let me take the text and check where can I write. Here is fine. No, here it's probably fine. Okay. So this is the exercise number 2, I think, of the TD. And it is a very simple model of financial exchange, or if you want, transactions. And you may look at the reference. So this exercise is taken from this paper that you find in the archive. 1912. 0.00359. So there are more details in here that you can easily look at. So let's introduce the model then. Okay, so as I say, this is a model for financial transactions. So what does it mean? Well, what it means is that as usual, you have many agents, or some agents. And these agents want to exchange a given financial product. So they want to buy or to sell some financial asset. It doesn't matter what this is. So for us, it will be something that they want to either buy or sell. So this can be stocks, bonds, whatever you can think of. And how do they do this? Well, they do not exchange directly, but the way they trade is by placing what people call an order. So they place orders. And an order is basically an intention to buy or to sell something. So an order is made of three things in general. So one is what I will call the direction. So you have to say whether you want to buy or whether you want to sell the given financial product. Okay. Then you have to specify what is the size of your order. So what is the amount of product that you want to buy or sell. And then you want to specify the price. So in general, what you say is, I want to buy, I don't know, 6 units of my given financial asset at a given fixed price. So you place this order into the market, and all of these orders are collected into what people call an order book. Okay. Which is just a collection of the intentions of all of the agents as we specified in here. So let me give just a sketch. So this is, you don't need to write this down. It's just to give an example of how we may think about this order book. So let me denote the agents with, I don't know, symbols. So there will be an agent that is a square, an agent which is a circle, an agent which is a triangle, and so on. And then let me take an axis, which is the price. And I divide this axis into slots. Okay. And for each of these slots, I put a symbol whenever the agent wants to buy or to sell the amount of quantity that we are thinking about at the given price, which corresponds to the slot. So suppose that the agent denoted with a square wants to buy something, wants to buy 3 amounts of this asset at this price in here. So I will put it here with the 3 squares. Then there is another agent that wants to buy 2 amounts of this thing at a lower price. And then, so as you can imagine, when the price is lower, these are the people that want to buy, that typically want to buy at a lower price. And then you will have, at a higher price, the people that want to sell. So let's say that the guy, which is the triangle, wants to sell 3 units at this price, and then there would be another one, I don't know, stars, that wants to sell at this price, and so on and so forth. And as you see, there might be a gap between the best price at which people want to buy, so the higher price at which people are available to buy, and the best sell price. So let me denote this price here at a given instant of time with BT, and let me denote this with AT. So there might be a gap between these two quantities, and this gap is what is called the spread. So the spread is S of t at any instant of time, and it is just the difference AT minus BT. Okay, so just one last thing about the terminology, just to understand the model. So this is discussed again in here. But so what I've been talking about so far are actually called limit orders. So I should add a limit in here. So a limit order is when you state indeed what is your intention. So you say, as I said in here, that you want to buy a given amount at a fixed price. But now there might be people that just want to buy or to sell a given amount at whatever price the market chooses for them. So there will be people that say, I really want to sell as fast as possible 3 units of this financial asset at the best price at which I find people to buy. And these type of orders, which are executed immediately, are called in this financial language market orders. So this means when you place a market order, what you're saying is that you want to buy or sell a given amount X immediately at any price. Okay, so this is a little bit just to give you the terminology of the more general models of dynamics of order books. And now what we are going to do the exercise, we are going to simplify the model quite a lot. So we want to simplify it in such a way that the only thing that we care about to describe the dynamics of the system is the spread. So it is just the gap between the best sell price and the best price at which people want to buy this particular asset. So how do we simplify it? So can I use that part of the blackboard? Yes. So we will make the following assumptions. Which define our model. So the first one is that the size of each order, we fix it to be equal to 1. So in this drawing, this means that each of these different agents can only buy or sell a fixed amount of this quantity. So we will have to adjust the drawing in such a way that you have only one symbol for each agent. Okay, so please stop me if this is not clear. In the meantime, I will write it. So size is fixed to 1. Then we make a second assumption, that is that once one slot in this price axis is filled, and you are a new agent that wants to place another order on top of what it is already contained in the book, you can only place it in front, so at a higher price if you want to buy, or at a lower price if you want to sell. So in front of those price slots which are already occupied. So once a slot is filled, place orders at only in the, let's say in the, let me write it, in higher or lower slot. Okay, so what this means is that the people that come first will occupy, so now I ran out of symbols, but let me repeat a little bit the symbols. But the idea is that the people who come first will occupy already all of the slots which are lower or higher. So this will be all occupied. And therefore, you get a model in which you essentially have no holes. So you can think of this in physics language like fermions. So you can put only one agent at each slot. They cannot pile up at the same slot. And if you want to add something, you have to add something either in here or in here. Okay. And then the third assumption has to do with these market orders that I just introduced. So a market order, so whenever somebody places a market order, this gets executed immediately. So he says or she says, I want to buy at this price. At this price slot, there is a guy that wants to sell. So whenever this happens, this guy sells the amount, and therefore this order disappears. So this means that orders are executed. So you actually buy or sell only at the boundary. So if you have a situation like this, the idea is that you cannot buy at this price. Whenever you really buy and execute the order, you do it at the best possible sell price. So why are we introducing these assumptions? Well, because once you have this, as you can easily realize, the only thing that can happen, so you have such a situation at a given time t, you assume that now there is somebody who wants to place an order, and the only thing that he or she can do is either to place an order inside the so-called spread, or to cancel one of the orders which are at the boundary of the spread, which means that all of the dynamics of this type of order book is encoded into the evolution of the spread of this difference. Okay, so I hope this was more or less clear, and now we are going to write formulas, so maybe it will become even more clear, but if you have questions, don't hesitate to stop me. So I think this gives a little bit of context, but in essence, the only thing that we have to keep in mind is that we have a model of order books where there are no holes in this price axis, and everything is encoded in the dynamics of this quantity in here. Okay, so now that we have this assumption, let's write down the model. So writing down the model means that now we have to specify what is the frequency at which we, or the agents, actually place their orders in the order books. And this is where we introduce these Hawkes processes that we have discussed in the previous exercise. Okay, first of all, a general question on the model. So we say that everything depends or is encoded in the dynamics of the spread. So now I basically said it already in words, but what are the events that decrease the spread, and what are the events that increase the spread in this model? And this is question 1. So anybody has a guess? Okay, so we basically have just 2 types of events. So if you execute or cancel, you can even cancel an order, then does the spread increase or does it decrease? Any guess? Okay, so if you go back to this picture, executing an order means that now I come into the order book and I say that I want to buy 1 unit at whatever is the available price. So I will buy 1 unit of my product at this particular price, which means that this order will be executed. And if this order is executed, you are enlarging, as you see, your spread. okay? Whereas if you place what I called above a limit order, then as I said, you have to place it in front of those which are already in there. So if I say that I want to buy, I will have to place myself in this slot in here, and therefore I will decrease the spread. Okay. So we have only these two type of possible events. And now what we have to say is what is the frequency at which this type of events or these type of events occur. And this, as I said, is modeled via these Hawkes processes. So there will be a rate for the events which increase the spread, and I will call it lambda plus. And this will be given by a Hawkes process. So the Hawkes process, as you remember, gives you the intensity in terms of a self-excited kernel. So there is first a term which is the so-called background intensity. So this, we call this mu before, but now let me stick to the notation of the paper. So this is a constant, lambda 0 plus. And then you have the term which contains the kernel that I will write in general like this. So this is a quantity which depends on time. So we have alpha. So now here we go again back to this issue of notations. So in the lecture, alpha was called beta, and we are going to call beta what was called alpha. So forgive me for that, but I think this is good because if you go back to the paper, at least you have the same notation. So we have this term in here where x of t, well, I will specify it later. So this would be the linear Hawkes process that we have discussed already. And then what we do is to add some small nonlinearity, which is important in here. So we add a term which is proportional to epsilon and which goes like x of t to the power of 2. Where what is x of t? Well, x of t is the usual self-excited exciting kernel. So this will be the integral from 0 to t in d tau of a function phi of t minus tau. So in the previous exercise and also later on, we are going to choose this to be an exponential. And then you have, so let me call the S the differential associated to this process. So what ds of tau tells you is what is the number of events that occur in a given small interval d tau of time. And I put a plus in here, and what I mean is that this ds plus of tau is the maximum between ds of tau and 0. So what do I mean by this? Well, what I mean is that the self-exciting part of the kernel is only or gets only contribution from those events that occurs at previous times that increased the spread. So if you have somebody that wants to execute an order and therefore increase this difference in here, whenever this effect occur, this will influence the total rate of your plus spread increasing events. But if you have an event that decreases the spread, so if somebody places a limit order, then this has no effect into this kernel. Okay, so this is for lambda plus. And then what about the others? Well, the others in the model, so the rate for limit orders is just taken to be a constant. So it's like it's a Poisson process if you remember from the lecture and from homework 5. Okay, so this is the model in full detail, the model of the paper. Now, what are we interested in? Well, we want to understand whether these models can give rise to crisis, and how can we understand how this crisis occur. So that's so this was point 2 of the exercise. And point 3 is how do we describe a crisis in this model? Well, a crisis in this setting means that you are in a situation in which dynamically you see that your spread starts increasing, and it increases without bounds. And if the spread increases, this means that this difference becomes larger and larger, which means that essentially you have no longer exchanges in your economy, in the sense that the people that want to buy at a price which is much lower than those that want to sell, and the people keep canceling their order or executing their order, and therefore there are no longer exchanges, and this is how you interpret that a crisis is occurring. So more formally, what this means is that x of t becomes infinite time. Which means basically that you start having an explosion of the events that are increasing the spread. Okay, now in the usual linear case, so let me just add this comment, when epsilon is equal to 0, we know one way to generate a crisis. So let's forget about lambda minus. So if we have just a Hawkes process, we know what is the limit in which the number of events is exploding. And this is the case in which, if you remember, this parameter alpha was going to 1. So the problem is well defined whenever alpha is smaller than 1, if phi is normalized to 1. And as you increase alpha and you get closer and closer to 1, the process becomes unbounded. And this is encoded in the fact that x of t explodes. So this is something that occurs already in the linear case. And now in here, we are going to see another way in which a crisis can occur, which is instead due to the presence of this nonlinearity, and which is related to this idea of metastability. Okay, so let's do this. So this was a little bit an introduction to the model. And now to actually do the proper calculation, let's simplify it further. So what we do from now on is forget about the events that decrease the spread. So I will put this lambda 0 minus exactly equal to 0. So after all, we are interested into this scenario of crisis. So we only want to care about the events which increase the spread. So I just simplify the dynamics. I set this to 0. And then I will denote the lambda plus simply by lambda. So I forget about, so the lambda t plus, let me simply call it lambda t. So in the end, we are going to focus on this nonlinear Hawkes process and see what's going on. Yes? Yes. So the question is that in here I should add, so the idea is that you can only place orders if you have a spread which is non-zero. So if in this drawing you are in a situation in which these two somehow collapse, then there is no space to place any further order in there. Yes, so you're asking why I don't put 1. Yes, okay, so that depends on whether, so what, since they cannot overlap, so I execute the order, if I have a guy in here that wants to buy and the guy in here wants to sell, then they match. I consider it in this way. So the question for those who didn't listen is the following. So in the text, indeed, I forgot that here you should put an indicator function that asks you that at the given time, the spread is larger or equal to 2. Because if the spread is equal to 1, so this means in our drawing that these are the people that want to buy and I have a guy in here. These are the people that want to sell and I have a guy in here. So yes, okay. So in here, in principle, yeah, this is a little bit of a choice. So in principle, you could place an order in here and then execute this. And this will give you immediately an event which is opening. So we want to forget about this. So we just ask that you have at least 2 slots so that if the guy puts an event in here, you're really decreasing the spread and you're not executing directly. So there is this little caveat in here. Thanks for. Yes, exactly. So the question is, why do we include this self-exciting dynamics in here? Well, I think that one way to think about this is that if you have some stocks or bonds and you start, so there is some sort of, let's say, dynamics, which depends on what the other people are doing, which is encoded in here. So the idea would be that if you see that many people are selling the stocks that they have because there is no longer trust on the company or on whatever is associated to the stocks, then you're also pushed to sell. And this is why, or to execute very fast your orders. And this is why you self-excite this type of processes. Okay. People online, please also stop me if something is not clear. Okay. Okay, so this was all basically introduction to the model. And now let's go to the actual math for this nonlinear process. And this is exercise 3, I think. Okay. So now we have, let me rewrite the process without the plus. We have this nonlinear Hawkes process, x of t plus epsilon x of t squared. X of t is my kernel, ds of tau. So that's the differential of the process. And as usual, we are going to make a simple choice for our kernel, which is the exponential. So we choose p of t to be beta e to the minus beta t, as we did in the linear case in the exercise of last time. Okay, so the first point of this exercise is to write down an equation for our dynamical variable x of t. And the starting point is as follows. So we are going to assume, so this is something that you can do rigorously, but I'm not going to do it in here. But what we are going to assume is that beta, which controls the decay of your kernel, is small. So whenever you say small, you have to specify with respect to what. So in our case, it would be, for instance, small with respect to lambda 0. Okay, which in words means that your kernel is slowly varying in time. So if beta is small, at least for the smaller times or for a window of time which becomes larger, this will be equal to a constant, or roughly equal to a constant beta. And whenever you are in this situation, what you can show is that you can simplify the dynamics of your process. So let me write it. You can assume that the dynamics of your process is given by a drift that is simply given by lambda of t, and a variance or a noise which has a strength which is of the order of square root of lambda t. So I will write it and then I will comment. So the assumption is that you can use that your dynamics ds of t looks like this. So you have a lambda t dt, and then you have a noise term square root of lambda t, and then eta of t. The dependence on t, I always put it as a subscript in here, but it's just a notation. So eta of t dt, where eta is the usual white noise. So what this means, so if you imagine that lambda is constant, then you will have a Poisson process. And for the Poisson process, you know that this would be true. So this is telling you that the average of your process is lambda, and the variance of your process is lambda again. These are precisely properties of your Poisson process. So this is like a Poisson. It has the same structure of a Poisson process, but now you have still this dependence on time in your rate lambda of t. And this is something that, as I said, you can argue more rigorously using the fact that beta is sufficiently small so that your kernel varies, does not vary very fast. Okay, so once we have this, then we can try to compute an equation for the changes in time of our variable x of t. So remember that to characterize crisis, we want to check whether x can go to infinity. So let's look at what is the dynamics of x of t. So let me write the differential of x of t. So to compute the differential, I have to take the derivative of this object with respect to time. So time appears twice. It appears as an extremum of the integration, and it appears inside of the kernel. So if I first take the derivative with respect to the extremum, this means that I have to compute whatever is inside precisely at the value tau equal to t. And if I do this, my kernel simplifies because the exponential of tau minus tau is equal to 1. So this first term will give me a contribution, which is beta times ds of t. And then I have a second contribution, which comes from deriving inside the integral. So I have to take the derivative of the kernel, and this will bring me down a factor of minus beta. So I will have from here minus beta times, again, the integral from 0 to t of, now I write it. So, okay, e to the minus beta t minus tau ds of tau. Okay. And if I look at my definition of x of t, then what I recognize is that this is precisely, wait, I forgot a dt because now I'm looking at the differential. So I have a dt in here, and this closes the parenthesis. So again, this is the derivative with respect to the extremum, and this is the derivative inside the integration. And what is this quantity in here? Well, this is just my original x of t, right? Because of how we defined it. Okay. And in here I have this ds, but ds, I just told you what is the form of the differential for ds. So what I can do is to plug this expression inside here and use the explicit expression for lambda, which appears here and here. So let's do it in here, and I hope that you can see.
I'm sorry.
Yes.
Sorry. Where do the two less expressions come from?
This one.
Yes, and the one above?
Okay, so this one is something that we are not proving. It is, let's say, an assumption. And if you really want to prove this, it takes a little bit of work. But what you have to use is that you're assuming that the parameter beta, which controls how fast your kernel is decaying, you're assuming that this is small, so that the kernel decays slower. And under this assumption, you can argue that the equation for your process, so this is what gives you the number of events that you expect to occur in a given interval dt, this can be written in the following way. So it has a drift term, which is proportional to your excitation rate, which is lambda plus. And then it has some noise, which is proportional to the square root of this excitation rate. And the way you can motivate this is having in mind a Poisson process. So the Poisson process would be the case in which alpha is equal to 0 and epsilon is equal to 0. And in that case, you know that the number of events in a small interval of time dt is Poisson distributed. So being Poisson distributed means that your average is equal to lambda 0 and your variance, so the sigma square, is again equal to lambda. And this is what is encoded in here. So in our case, we do not have really a Poisson process, but we are somehow assuming that this lambda of t changes very slowly. So we can kind of think at it as a constant. And this is why eventually you get out this expression in here. But this we are not proving this. Let's say this is what we are assuming. And once we assume this, then we can write down an equation for the x. So where does this come from now? So I want to write a differential for this quantity, x of t is given in here. So what I have to do, so I could write directly the derivative over time, and now I'm writing it in the differential form. But you see that if I take the derivative over time of this expression, I have that the time appears both in here and appears inside the kernel. So when I derive, I have two contributions. So the first contribution comes from evaluating the integrand, the quantity which is inside the integral at the time t. And this is this quantity in here, right? Because if you evaluate the kernel at the time tau equal to t, then this is like evaluating phi at 0. So you get a factor of beta. And then this ds of tau becomes ds of t. Okay. And then the second contribution to the derivative, I keep the integral as it is, and I take the derivative of the kernel itself with respect to t. And this is the expression that you see in here. So if I derive this with respect to t, I get a factor of minus beta that I am collecting outside with a minus sign. And then the rest, I recognize that it is just x of t. Is it clear?
Yes, it did. Thank you.
Okay, great. Okay, so now let's try to write this in a way which is cleaner. So I have this beta. Then I plug the expression for the s of t, and I plug the expression for lambda itself. So let me try to collect everything. So I have a lambda 0 dt. Well, let's do this. I have a lambda 0 plus alpha xt dt, which comes from here. Then I have the noise, so sorry, I forgot the epsilon plus epsilon xt squared times dt. The noise, I will write it as a last contribution. Let me write this. So then I have minus beta, sorry, the beta minus x of t times dt. And then I have the noise, which is encoded in here, which was square root of lambda. So I will write it as plus square root of lambda t eta of t dt. Okay. And now that I have this, so now you see that this is now a closed equation for x. So let me try to rewrite it in the way we wrote the Langevin equation before. So Let me try to write it. Now I divide by dt if you want. So I want dx t over dt. So let's collect everything. So I have a lambda 0 beta. Then I have a linear term. So there is a factor of beta always in front, and the linear term is alpha minus 1. So this is minus 1 minus alpha times beta x of t. Then I have the nonlinearity, beta epsilon x of t squared. And then I add the noise, plus beta square root of lambda t eta of t. Okay? And now what I want to do, as before, is to write this quantity in here as the derivative of some potential. So as minus the derivative of some potential that I call V, which depends on x, derivative with respect to x, evaluated at x equal to my dynamical variable x of t. So this will be the gradient descent term, and then we will have a noise term, as it was done in the case of the magnetization in the lecture. So what is the potential? Well, what I have to do to recover the potential is, so this is minus its derivative, so I have to integrate this expression with respect to x, sorry, so I will have, well, a minus sign in front. Then lambda 0 beta integrated with respect to x will give me lambda 0 beta x. Then I have something that is linear, so the integral will be x squared over 2. And then I have the quadratic term, which will give me x cubed over 3. So if I now take minus the derivative of this object, I recover what I have in the right-hand side. You mean that, yes, because I killed all the events which decrease the spread by setting lambda 0 minus to 0. So the question is, why don't I put in here the constraint, or it was actually inside x, that ds is actually ds plus, so it counts only the spread increasing events. And the reason is that to simplify the model, I kill the rate at which the spread decreasing events occur. So I set lambda 0 minus to 0. So all of the events which occur are those that increase the spread. So my ds coincides with ds plus. But thanks for pointing out. Okay, so now this is our potential, which depends on our nonlinearity epsilon. And now to try to understand the dynamics, what we have to do is to study this potential. So let me rewrite it a little bit. So let me write this as beta 1 minus alpha over 2. And then I want to compose these two terms in such a way to have a global square. So I will write it at x minus lambda 0 over 1 minus alpha square. So if I take x squared, I recover this. If I take the double product, I recover the linear term. And then I have a global constant, which I have added that I will need to subtract. So first I put the cubic term, and then let me subtract the remaining term, which I just added. So this will be lambda 0 squared beta divided by 2, 1 minus alpha. But this we don't really care about it because it's just a global shift, it's a constant that will not matter when we look at the shape of the potential. Very good. That's important. Okay. Okay, so let's study this. And let's start from epsilon equal to 0, where we go back to our linear Hawkes. So I will forget about the constant term. That doesn't really matter. So in the case epsilon equal to 0, then the shape of our potential is simple, because I'm killing the cubic term and I just have essentially a parabola. So if I plot v epsilon equal to 0 of x plus the constant lambda 0 square beta over 2 1 minus alpha, then I have a parabola, and the center of the parabola is a quantity that you might recognize. It is lambda 0 divided by 1 minus alpha, so my potential will look like this. Okay. And so is there anybody who recognizes what was this expression for the linear Hawkes process? So I'm changing the notation, so maybe that's a bit. So that was in the exercise of last time. That was mu over 1 minus beta. But anyway, if you go back to that notation, you will recognize that this is the average intensity of the linear Hawkes process. So this was, if you want, the average of lambda t, or sorry, in this notation, it was the average of ds of t actually. Okay. Which was also the stationary value. So there was, if you recall, if you remember, there was a discussion about the process being stationary for alpha smaller than 1. So the value at which this rate eventually converges was given precisely, or was related to this expression in here. And this is good, because what we recover with this potential description is precisely this. So in here, if you think at the process in terms of this Langevin dynamics, then what do you expect to happen? Well, you have just one minimum. So your dynamics will have some noise, will descend because of the gradient term, and eventually it will relax into this unique minimum that is what will govern your stationary state. So if you ask what will be the stationary value of my x of t, then this, because of ergodicity, if you want, this will be given by, so I'm just, this is just a definition. Then remember that you have here this ds of tau. So at very large time, you expect that this converges to the average of this quantity. And if you take the average, what you have to average is this ds. And if this average of ds converges to this quantity in here, using then this is independent of time, you bring it out of the integral, the kernel is normalized. So what you get is precisely that the long time limit of your value of x coincides with this expression in here that we had already computed. So this is consistent with our previous analysis of the linear Hawkes case. But now if you add epsilon, which is positive, of course, this picture will change. And it will change because if you add some nonlinearity, there are more stationary points of your potential which appear. So let's compute them. So now let's look at epsilon larger than 0. So how does one compute the stationary points of the potential? Well, what you have to do, so stationary points are the minima or the maxima. So to compute them, what you have to do is to take the derivative and set it to 0. So the derivative, we have it in here, up to the minus sign. So we have to compute those values of x where this expression is equal to 0. So this is a quadratic equation for x that we can solve. So let me just give you, being it quadratic, it will have two solutions. So let me give the two solutions directly. So this will be 1 minus alpha plus minus square root of 1 minus alpha squared. So the beta simplifies, and you get something like this. Okay. So these points will be stationary, meaning that they are either maxima or minima. And now, what should you do to understand which one is the maximum and which is the minimum? Any guess? So in general, the way in which you distinguish whether you are in a minimum or in a maximum is to look at the second derivative, right? So if the second derivative is positive, you are in a minimum. If the second derivative is negative, you are in a maximum. Now here you can compute the second derivative and check the sign when you evaluate it at this point. But let's do a shortcut. So what is the shortcut? Well, is to understand, is to use what we already know from epsilon equal to 0. And to guess what is then the shape of the potential for epsilon different from 0. So this will be now VE of epsilon plus the constant. So before this was a minimum, now we switch on epsilon. So first of all, as you see, if you take x, which is very, very large, the term which dominates in this expression will be the cubic term that has, quite importantly, the minus sign in front. So what this is telling you is that for x very, very large, this potential will decay like minus x cubed in here. And then you know that you have two stationary points, so it is quite easy to expect. If you study the behavior at x equal to 0, you will find something like this. So it is easy to expect that your potential will have some shape like this, with a minimum and then a maximum that allows you then to decay to minus infinity. So we have to understand which one is x minus and which one is x plus. And a fast way to do this is to try to look at the behavior of this quantity when epsilon is small, because we know that when epsilon is 0, the minimum will collapse to lambda 0 divided by 1 minus alpha. So let's expand these two terms, these 2 points for small epsilon. So if I look at the term with a plus, when epsilon is 0, I can kill this term inside the square root. I just have 1 minus alpha to the power of 2. Its square root, so this quantity is positive, so it's just 1 minus alpha. I have a plus, so I have twice 1 minus alpha divided by epsilon. So this will go, when epsilon is very small, like 1 minus alpha over epsilon. And this is x plus. Whereas if I look at x minus and I do the expansion, I have to be a little bit more careful, because then the order 1 terms will cancel because I have a minus. So I have to keep also the expansion to order epsilon that comes from expanding the square root. Okay, and if I do this, so this is, you can do it formally. So this will be 1 minus alpha. I just look at the numerator now, plus minus 1 minus alpha. So I bring 1 minus alpha outside the square root, and then I have 1 minus 4 epsilon lambda 0 divided by 1 minus alpha square. And then if epsilon is small, I can expand this square root. So this is 1 minus x to the power 1/2, and the expansion for x being small is, so this will be, the expansion of this is 1 minus 1/2 times x, as you can check. So if you do this in the limit epsilon being small, you find that this is precisely lambda 0 over 1 minus alpha plus terms which are of order of epsilon. Whereas in here you have plus terms which are of order 1. So this is to say that by continuity in epsilon, we expect that the point which is the minimum is x minus. So this here will be x minus. That when we switch epsilon to 0, will collapse to this point in here. Whereas the new stationary point that we have is x plus, which, as you see, is very far away if epsilon is small, because it is of the order of 1 minus alpha divided by epsilon. Okay. So this tells you that in the limit epsilon going to 0, this goes to infinity, and you recover this picture with a unique minimum. Okay, so the last thing that we need to understand the dynamics is then to compute the barrier. And the barrier is a measure, so what we can do is to compute then the value of the potential at this local maximum. That tells you, so if you shift the potential, this is actually 0, so it tells you what is the barrier, what is the difference in potential that you have to overcome with this type of jumps or activated processes. So this means that we want to compute V evaluated at x plus. So this is algebra. It's you can do it. So let me go a little bit fast. I will expand it. So this is, no, I don't expand it. This is exact. If you do the math, you will find that this barrier goes like 1 over epsilon squared. So when epsilon is small, this point is very, very up. This is very, very large and very, very far away. So this barrier here, delta V, is of the order of 1 over epsilon squared. And so again, what happens? You take epsilon going to 0, this x plus goes to infinity, the barrier shoots up, and you recover, as you see, the nice parabola that we had before. Okay, so this is the potential, and now that we have the potential, we can ask this question about activation. So in a similar way as for the double well of the magnetization, of the easing, we can imagine that the dynamics, if you start from somewhere within the basin of attraction of x minus, will relax in this metastable state, but then there will be very rare activated processes that kick you up across this barrier. And once you go across this barrier, then you start rolling down, because from there on, the potential goes to minus infinity. And therefore, if you manage to kick this barrier, then you go into this scenario in which you have a crisis of your economy or of your financial exchanges that, if you remember, was defined by X exploding and going to infinity. So how often does this happen? Well, we can use results in the literature to compute what is the average time that is required to see this type of jump events. And there are explicit expressions for this. And for this particular example, the expression for the time is given in full detail in the text of the TD. So this is now 0.3. Okay, so if you look at there, what you see is that you can write down what is the average time for these activated jumps. which will be given by a prefactor that I just call a. I am not going to rewrite it, so that is the square root that you see in the text. And then you have the exponential, that is what we want to compute, of what? Of an integral. So the integral goes from, so in the text I wrote x equilibrium and x star. So what I mean by this, x equilibrium is x minus, is our metastable minimum, and x star is the point where you have the barrier. So let me call it x minus and x plus in the x. And then you have a ratio. So you have the ratio between the derivative of your potential, v prime of x, and another quantity that is called d of x, that if you look at it, you will recognize that it is basically the variance of the noise of our Langevin process. So d of x is v square over 2 lambda 0 plus alpha x square, sorry, x, plus epsilon s x square. So this was basically lambda t. And if you look at your Langevin in here, it is basically the square of this expression. So it is the variance of the noise. Okay, so to compute this time, what we have to do is to compute this integral, which is at the exponent. So this is a little bit lengthy, so I will not do it in detail, but you find it in the solution. Maybe I will just give you an idea. So, and the idea, so it's lengthy because, well, you have to integrate on a finite interval the ratio of two quantities which are quadratic. So what's the fastest way to do this? Well, I think that the fastest way is, first of all, to look at the denominator and try to write it as a sum of two terms which are only linear in x. So to do this, what you can do is you compute the roots. Now I will sketch just how to do the computation. So you compute the roots of this expression. Let me call it x1 and x2. So you set this equal to 0 and you will get two values for x. And then you can show that you can write 1 over the x as, so if you compute the root, then you know that the x is essentially equal to a constant. So dx will be some constant, x minus x1, x minus x2, right? And the constant is chosen to adjust the coefficient of the term x squared. So you plug this into the denominator, and then you try to split these two terms into a sum of two terms which are only linear in the denominator. And you can do this. You will find that you will have an expression like this. You have a prefactor, and then you have 1 over x minus x1 minus 1 over x minus x2. Okay. And this helps because now let me call this integral at the exponent curly I. So this expression is the coefficient times the exponential of the integral. So then you can write your integral as what? As the prefactor times the difference of two integrals, one which contains v prime of x, x minus x1, minus the one which contains v prime of x, x minus x2. Then what you have to check is that x1 and x2 are always smaller than x minus. So you see you have in principle a singularity, but this is outside the domain of integration. And then you can, this integral is something that you can do quite easily. So now you have a quadratic form in the numerator, and you can rewrite, so that's just the hint for the math, but you can rewrite v prime of x as x minus x1. So suppose that we want to do this integral. What I have to do is to play a little bit with my v prime of x, and I can rewrite it as a constant times x minus x1 square plus another constant times x plus another constant. So this is an exercise. And once you rewrite it in this way, you plug it in here, and you see that you have either terms which are linear in x, or the only most non-trivial term that you get is of the form gamma over x minus x1 that will give you a logarithm. So if you do these tricks, you can compute these expressions quite easily, but I'll leave it to you, and you can of course check the solutions. And now let's comment what comes out of this. So doing all of the math, and then doing an expansion for small epsilon, which is what we are interested in. The expression that you get is as follows. So you get that this E of tau, or actually the integral that you have at the exponential, will go like alpha square minus 1 minus 2 alpha log alpha divided by alpha beta epsilon, plus you have logarithmic corrections in epsilon, plus terms which are regular when you send epsilons to 0. Okay. And of course, I am assuming here that alpha is different from 0. If alpha is equal to 0, you will have to redo the calculation with a little bit of care, but you get a very similar result. And so the important point, and with this we can conclude, is that you find then that your average time for your escape or activated processes goes like e to the some constant times 1 over epsilon. And so again, when you take epsilon to 0, you see that you recover the situation in which this time explodes, and you cannot have any of these activated processes. But as long as epsilon is finite and you have some nonlinearity in your process, you go back to this metastable situation. So you have to wait a very large time, but eventually you have situations in which the noise kicks you up this very large barrier. And if this happens, then after that, you are bound to roll down to minus infinity, and therefore you have a crisis for your economy. And this is a scenario that is different with respect to. So let me add 2 comments. One on the content, which is the last point of the exercise. So this is a scenario for the crisis that is different with respect to what we have already discussed. That was the case in which alpha is very close to 1. That is what was called in the literature as self-organized criticality. So it is different because in this scenario in here, you have an economy or whatever you are describing that is always at the verge of being critical. So any small fluctuations will pull you into the unstable phase where alpha reaches 1, and then you have an explosion in the number of events. Whereas in here, you have something very different because you have a state, a local minimum that actually looks quite stable, and it looks stable for very large times. So you are in this economy and you think that everything is going well because you are in your metastable local minimum, and you have no clue. So your parameter alpha is very far away from 1, so you have no clue that something could go wrong. But just because you have this little nonlinear term, eventually, if you wait long enough, then your noise will actually bring you uphill in here and will lead you to a crisis which is very hard to predict a priori if you don't have this picture in here in mind. So the scenario for the behavior of the system is really very, very different. This is a crisis which is due to activated processes, whereas if you choose alpha close to 1, you go back to this idea of self-organized criticality. And the second comment that I wanted to just point out, and then the details you can figure them out, is that this matches the calculation that we just did. So in particular, this time going like 1 over epsilon matches with the scaling that I wrote at the beginning for the easing-like case, which was that this time was going like the barrier inner potential divided by the variance of the noise. Why is it so? Well, because in here, so it might be a bit surprising that you have 1 over epsilon, because if you remember, the height of the barrier was of the order of 1 over epsilon square. So you would expect a priori a 1 over epsilon square in here, but the point is that you have to be careful about the noise, and the noise depends on the particular point x where you are, because the noise in our Langevin equation was the square root of lambda t, or was going, let's say, the variance, what I call sigma square there. In our problem goes like lambda t, and lambda t goes like lambda 0 plus alpha x plus epsilon x squared. And what you can check is that if you compute this expression at the barrier, which was x plus, you see that this goes like 1 over epsilon, if I am not mistaken. Well, this we can check. So this should go, when computed at the barrier, it goes like 1 over epsilon. So if you plug it into this expression, you will have dv, which is 1 over epsilon square. And then you have a factor of, so you have a sigma square, which is, or sigma square over n now becomes 1 over epsilon. And combining these two scalings, you get out precisely this factor of 1 over epsilon for the relaxation time. Now, this is not quite the right argument, because the noise changes all along the potential. So to recover the scaling, I computed it only at the barrier. But what you have to do properly is precisely what I sketched in here. So you really have to compute this integral all over your path. So what I'm saying is that if your noise is constant, you could bring this out of the integral, and then you just have the integral of a derivative, which gives you the difference of the potential at the 2 points. So that will be the barrier divided by d, if d was constant. Now here d is non-constant, so you have to go through all of the integration, which depends on x, but you somehow recover the scaling if you just compute d precisely at the point which corresponds to your barrier. And so you see that you have an expression which matches with what we know from the lecture. Okay, so I think now we can maybe, so this was it for this exercise on metastability. Are there questions? Okay, if there are no questions, I think we can maybe make a break now and then go to the second part, if you agree. So now is 10:40, so we can have 15 minutes of break, and then we go to part 2. Okay.
This conference will now be recorded.
Okay, good. Good, so let's start again with part 2. And the text is in the TD 7/8. And what we are going to discuss in here is something which goes under the name of imitation models or models for herding, or even, well, let's say imitation models. And in particular, we are looking at a particular model that was introduced by Kirman in this paper of 1993. And the motivation of Kirman, so this is called the ants model, so ants like the animals. And his motivation was to understand indeed behavior of animals. So the idea is that if you have this collection of animals and then you put two sources of food, what he was realizing is that these animals always somehow choose to go to eat either in the source A or in the source B. But sometimes there are some very abrupt changes where all of the animals suddenly want to go to the source A, or all of the animals want to go to the source B. And so the idea was to write down a simple model to try to understand this type of, if you want, collective behavior or behavior of a large number of agents. And we can generalize it a little bit, so we can think of this as being a description also of human behavior. So whenever you have a choice between two, a binary choice between two options, and there is a huge amount of people that have to make choices, sometimes you see that you have these abrupt switches between one choice or the other. And we would like to understand why this happens and what is a good description for this. So this could also be in economic trends where you have some reversal of the behavior of people. You can also, so it was mentioned in the lecture, this example of using cell phones. So people have to choose whether buying or not a cell phone, and this can change massively over time. So these are all things that we can think of in terms of these very simple models. So the Kirman model that we are discussing today, you also find something about that in the lecture notes. So I uploaded yesterday night a new chapter, which is a chapter which is about random field leasing model, and which contains something about what we are going to discuss today. And a model which is similar is the Moran model that, if you have time, you can look at in the homework number 7. And again, I will upload the solutions after the TD today. So let's describe the models. So what are the rules of the game? So the idea is that you have, again, many agents that interact with each other, and which are of two types. So rules of the game. So you have two species, if you want, A and B. So this can denote, I don't know, the people who want to buy a cell phone and the people who don't, or the people who want to vote for something and the people who want to vote for something else, and whatever you want to think of. The ants which want to go to the source of food on the right versus those which want to go to the source of food on the left. And all of these individuals interact in the following way. So there is, they meet. So let's choose a typical time scale, so an interval of time, dt. And what happens is that we assume that, well, these people or these agents can meet with each other within this interval of time in pairs. And they meet with a rate. So the rate of, let's say, meetings, we denote it with gamma. And whenever they meet, if they are of a different type, some discussion takes place. There is some influence of one on the other, and there can be some conversion. So you can have, let's say, some conversion. So the conversion means that you have two individuals one of type A and one of type B that meet together with a rate gamma, and as a result, either the individual of type A is able to recruit the individual of type B in its team, or the vice versa can occur. So you have a process in which you start from this configuration and you end up in either one of these two configurations. And in this model now, we assume that this happens with equal probability. Whereas if you look at the Moran model, well, you have some fitness. So if you look at the homework, the situation is a little bit different, but let's stick to this example for the moment. So you have some conversion which can occur with rate gamma. And you also have something else. So you can have that some individual decides to change its team spontaneously. And this also happens with a fixed rate, which I call in here epsilon. So this will be, so let me put a slash in here. You have a rate of, let's say, self. Okay. I'll write it properly. So you have conversion and you have what I can call self-switching. Self-switching means that without meeting anybody else, an individual of type A can decide to become of type B and vice versa. And this happens with a rate that I call epsilon, and I call it epsilon for a reason that we will discover afterwards. Okay, so these are the rules. And now, well, before going to the exercise, let me stress something. So we are going to solve these models. And from the technical point of view, what will be important in here is what I will discuss in point 2 of the exercise. And the idea will be to go from a discrete setting, which is the one that I'm sketching in here, to some sort of continuous limit, which in essence means that we are going to start from some master equation with transition rates, and then we will try to derive from that a kind of Fokker-Planck equation for the process taking a continuous limit. And this I will do a little bit in detail, and I think it is important for you to have a look at how you can do this properly. But this is point 2. Now let me start from point 1. So point 1, which allows to understand a little bit better what I wrote in here. So the idea is now to describe this process in terms of transition rates. So let me fix one type. So let's choose type A. And let me introduce a variable k. So k will be just the number of individuals of type A out of n. So let's say that we have a total of n individuals. So as you see, with this type of dynamics, n remains constant because every time two individuals meet, they can change their opinion, but you end up with two individuals at the end. So n remains constant, and k is the number, is the variable which changes with time, which denotes, if you want, the number of individuals of a given type. And then we write down transition rates, which tell you what is the probability that you increase or decrease this value of k. So I will call them W, as it was done in the lecture. So W will be the transition rate to go from k, for example, to k plus 1. And what a rate means is that this is a probability divided by time. So if I write it as W times my small interval dt, then this will be a full probability. So this will be the probability that over a small interval of time dt, I go from having k individuals of type A to k plus 1 individuals of type A. And if you look at the model, what we are always assuming is that the interval is chosen in such a way that you have at most one encounter between two individuals at each interval dt. So what is this rate? Now this is given already in the text. So let me write it in a slightly different way and let me comment. So this is 1/2 times gamma. And then you have phi. So phi is defined as a fraction. So I will write it as k over capital N. 1 minus k over capital N plus epsilon 1 over k over capital N. So indeed, what this is describing is what we just said when describing the model. So the idea is that in this small interval of time, two individuals can meet, and they will meet with a rate. So let me erase the dt here. So two individuals will meet with a rate gamma. And if they meet, a conversion can occur only if they are of different species. So you need that one of those is of the species A, and this will happen with a probability that is equal to the fraction of individuals of the species A, so it's k over capital N. The other one has to be of species B, so this is the corresponding probability. And then when they meet, a conversion will occur, and the conversion can be, so you have an equal probability that the conversion is good for the individual of type A, so that the type B converts and becomes type A, and therefore you increase your population, or the conversion can go on the other side, but the probability for the good conversion to occur is encoded in this factor 1/2 in here. So the first term is describing when you increase your population because of this recruitment or interaction effect. And then, as I said, you have this extra contribution of the self-switching. And this, of course, has to be proportional. So this will occur with the rate epsilon. And it has to be proportional to the population of type B, because only those of type B will convert to type A and increase your population. So this is essentially encoding just the rules of the game that we wrote upstairs in words. And of course, you have the other way. So you have the rate of decrease of your population. And now, as you can easily guess, the first term will be exactly the same. So you have the same probability that two individuals occur, and now you have the conversion of both to type B, which decreases your population. Whereas in here, to decrease your population, you need that an individual of type A converts to type B, and this happens with a rate which is epsilon and with a probability that is equal to the fraction of individual of type A. Okay, so this is essentially what encodes the dynamics of your model in a small interval dt. And now from here, what we want to do is, so if you have these rates, you can write down some generic master equations for the behavior of your probability. So let me call it P of k at time t. So this is the probability, of course, to have having k individuals of type A at time t. And the master equation will contain the transition rates. So if you want, we can write with this type of notation, we can interpret our transition rates times the small interval dt as the conditional probability that you are at k plus 1 at time t plus dt, given that you were at k at time t. Okay, now I will not write down, well, yes, I will do it in a minute, or actually, let me do it. So let me write down a discrete master equation for this process. Do I have space? I think so. So I ask, what is the probability that at time t plus delta t, I have k individuals. So this will be equal to the following. So I have a certain probability that at the previous time I already have k individuals. And then I'm asking that nothing happens in the interval dt, so that the situation remains unchanged. And the probability that nothing happens is 1 minus the probability that something happens. So this is 1 minus the probability that two individuals meet and switch, and one of those switches. And this is gamma k over n times 1 minus k over n. And then I also have to subtract the probability that one of those switches by itself. So I remember I add the dt because gamma is always a rate, so it has a dimension of 1 over time. And the probability that one of those switches is just epsilon dt. Okay, so this is the contribution when nothing happens. And then, of course, you have contributions to this probability coming from a conversion, which occurs in the small interval dt. So you will have here a plus the probability that you were at k minus 1 at time t, times the probability that somebody converts to the type A during the small interval dt, and this is precisely given by the rates that we wrote before. So I will write them compactly. So this is W to go from k minus 1 to k times dt. Okay. And then you have the term coming from above if you want. So you have to add the probability that you were at k plus 1 at time t, and then somebody goes to type B, which is the other rate. Okay, so all of this is in the discrete setting. And now to do exercise 2, so I'm modifying it a little bit with respect to the text, but the idea is that I just want to show you a little bit how one goes from the discrete setting to the continuous Fokker-Planck-like equation. So we will do it in 2 steps. So I will first sketch how you do this properly, and then I will sketch a shortcut that uses some of the things that we discussed in TD3 and also very briefly at the end of the last TD. Okay, so the point 2 is go to the continuum. Which means that we want to take the number of animals or people or agents going to infinity and write down an equation which holds in this limit. And to do this, we have to introduce some continuous quantity, which are kind of what you introduce whenever you look at this n going to infinity limit. So you introduce densities and you try to develop a description in terms of density, like the magnetization as we did for the spins. So let me introduce this quantity phi. So phi will just be the fraction k over n. And let me also introduce something that hopefully will become clear in a minute. So I will also think at the fact that if I want to develop a continuous description, I not only have to rescale k to be able to send n to infinity, but as we will see, I will also have to rescale time to have a properly defined equation. So I will write it down here and then we will see this in action concretely. But the idea is that I will need to rescale my time variable with a given power of n, which for the moment that I will have to choose. to get a well-defined limit when n goes to infinity. So for the moment, let me write down a generic power n to the alpha. And then what I want to do is that I want to show that I get a well-defined equation, which will be of the Fokker-Planck type, for a new probability, which it's now a function of this continuous variable now, phi, and of my rescaled time, and which I can think as the limit when n goes to infinity of the probability of my discrete process evaluated at k, which is nothing but n times phi. So this is a bit formal, but then we will see what I mean. And at the previous time t, which is rescaled with respect to the one of the continuous process. So I will start from my master equation for this capital P, and then I will try to write it down in terms as an equation for a function which is always a function of only a function of phi and of some rescale time. And I will see if doing that I can reach, I can take then the limit and go into infinity and find a closed equation for this quantity in here. So this is all in words, but I think it's much clearer if one does the calculation directly. So to do the calculation, let me start from the master equation up there. And maybe I go down here. Okay, so you see that you have P of k t plus dt, and then on the right hand side you have P of k t plus something which depends on dt. So the idea is that I want to get on the left hand side some derivative. So I rewrite that as P of k t plus dt minus P of k t divided by dt. And then I start manipulating what remains on the right hand side. And I started doing that. So since eventually I want to introduce this variable phi, let me try to introduce, to rewrite what I have on the right in terms of phi. So let me try not to do mistakes. So the first term which I get is a minus gamma. Then I have the fraction, which is precisely phi. Then I have 1 minus phi. And then I can also put plus epsilon in here. And everything is multiplied by my probability of k and t. And using now for this type of relation for finite n, what I can say is that in the limit, okay, so I will write it down, and then, so the idea is that you have in mind that you will take the limit and go into infinity of what you have on the right hand side. But if you take the limit and go into infinity, this p, you expect it to converge to a function which is a function of phi and tau. And so I will write it here. So this will be my p of phi and tau in terms of t. Since I have t, still t on the left hand side, let me keep t. So this will be t n to the minus alpha. So if you see P of kt is precisely this, then I am assuming that this has a limit when n goes to infinity. So I replace, I take the limit on the right hand side and I replace with my limiting function curly p. But then if I look at what I have below, things are a little bit more complicated. So now we have to remember which were the rates in there, but are a little bit more complicated because, so what was W? So this was W going from K minus 1 to K. So you have to look at this expression in here, and you have to replace K with K minus 1. So I will write just the first term. So I will have in here plus, what is the rate from K minus 1 to K? So it's the constant terms, so is 1/2 gamma. And then since I'm starting from K minus 1, instead of K over N, I will have K minus 1 over N. So K minus 1 over N is phi minus, is phi minus 1 over N. Do you agree? Because K over N is just phi, and then I have a 1 over N. Then I have 1 minus K minus 1 over N, and this I can write as 1 minus phi plus 1 over N. And then the same thing for the term with epsilon. So this will be plus epsilon. Yeah, sorry for the spacing, but you have the same thing. You have 1 minus phi plus 1 over N. Then I close the parentheses. I don't know if you see this, but all of this thing in parentheses then is multiplied by what? Well, in principle, I have capital P of K minus 1t. So let me rewrite it. So let me assume that N is large. And this I can rewrite basically as my curly P evaluated at what is K? So K is, so this is, if you want, N over phi minus 1. So I can rewrite it as N times P minus 1 over N. And then I know that my probability P as a function of N times something will map into my function curly P evaluated at the something. So let me write it down. So this will be phi minus 1 over N. And then I have to rescale time as above. Okay. And now I have then the other term. So the other term is quite similar, except that this rate in here is changing. But if you do this along the same line of reasoning, you have, well, the first part of the rate is unchanged. And the second part was just multiplying. So now you go, no, it was not unchanged because I have a plus somewhere. Okay, so to compute the second term, you have to evaluate the rate now, which goes from K plus 1 to K. So if I use the expression that I wrote before and I do the same expansion, you realize that I have a plus in front of the correction because it's K plus 1 and not K minus 1. So you should find something like this. Please stop me if this is not immediate, and I will do it explicitly. And then the term in here is proportional to K plus 1 over N, which I will rewrite as phi plus 1 over N. Times my curly P, which now is evaluated at K plus 1, which in my new variable is phi plus 1 over N, and then the rescaled time. Okay. Yes, this is minus, yes, because I have a minus in front. Thanks. Exactly. Okay, so now I'm doing things a little bit sloppy. So as you see, I'm translating from one notation to another and taking first one limit before the other. But so you can do things more properly. But what I just want to emphasize is the step that comes now. And the step that comes now is that you now have, so you rewrite things in such a way that on the right-hand side, it appears the function of which you want to compute or for which you want to compute an equation. The left-hand side, we have to work on that, but we will do it last. But the point now is that this function is now computed at phi, which is good. But then you have this correction of 1 over n. And so what we can think of is now to do an expansion of what appears in the right-hand side in powers of 1 over n, which is our small parameter when n goes to infinity. So I'll just give the idea. And then we will not do all of the calculations because it's a bit tedious, but let me give the idea. So now you assume that you can expand your function. So whenever you have p of phi minus 1 over n, and my t to the n minus alpha will be what I will later on call tau. This you will write as p of phi tau, and you're happy with that. Then you have the first derivative over phi times minus 1 over n. So let me put, and this is evaluated at phi and tau times 1 over n. And then it turns out, for a reason that you realize when you do the calculation, that you have to go to second order here. So you will have a second derivative to keep into account with a 1/2 in front. 1 over n squared. And of course, you do the same whenever you have p evaluated at phi plus 1 over n. And now what you have to do is to plug these expansions on the right-hand side, combine all of the terms. So you see that also the rates will have a term which is of order 1, which just depend on phi, and then we'll have terms of order 1 over n and terms of order 1 over n squared. And you have to collect everything to expand your right-hand side in powers of 1 over n. Now, if you do this is a little bit lengthy, but what you realize is that many terms will cancel. So in particular, the term of order 1 of order 0 and the term of order 1 over n will exactly cancel from this expression. And so in the end, you end up with the following thing. So let me keep the left-hand side. Which was this. And then on the right-hand side, so if you trust me, you will see that you reduce everything to the following. So you have a 1 over n squared times the second derivative of your original rates times now your function evaluated at phi tau. Minus, so plus minus, nope, a term which looks like this. So there is a term 1 over n epsilon d over d phi of 1 minus 2 phi times your p. Okay. Okay, so you have something that on the right-hand side has some scaling with n, which remains non-zero, but the scaling has some mismatch. So you see that you have a 1 over n squared times what you would like to have, quantities of order 1 in the limit n going to infinity, minus 1 over n instead times quantities of order 1. So in order to get a meaningful right-hand side limit of this equation, I have to do an extra step, which explains why I choose this notation epsilon. So I have to assume that epsilon also scales whenever I look at this continuous limit. I have to assume that epsilon also scales like 1 over n. So I say that epsilon is equal to some constant E0 divided by n. And in this way, E0 is of order 1, and I match the scaling between these two quantities. So why do I do this? Well, if you think about the usual mean field or fully connected things, you realize that this is actually the meaningful thing to do. And the reason is that, so usually whenever you have these interaction terms and you have a scaling with n, you have to rescale with the interaction to have something which remains of order 1 in the limit n going to infinity. But anyway, in here you see it directly from the calculation that in order for these two terms to match, you assume that epsilon when n goes to infinity scales as 1 over capital N. And if I do this, then I can replace here. So let me erase this. I put an epsilon and I put an n squared. And I have a global factor of 1 over n squared on the right-hand side that I simply bring on the left-hand side. So I will have a dt divided by n squared in here. So of course, this can be done properly and rigorously, but let me just give you roughly the idea. And so you see that now my right-hand side looks like a properly well-defined Fokker-Planck equation with a drift term, which is of order 1, and with a diffusion term. And my tau, I define it as some rescaled time with an unknown power n to the minus alpha. And in order to make sense of this equation, what I want from the left-hand side is that I can rewrite this as the derivative of my p with respect to the same tau variable. So the dependence on k is fine. You have k on both of these terms. So this, once I rescale, will become just a function of phi. I don't have factors of plus minus 1 over n to care about. But you see that what I have to do in order to for this mapping to make sense is to choose my power alpha in here in such a way that I can rewrite the derivative over t, if you want, which is related to the derivative over tau by 1 over n to the alpha. I have to choose that alpha in such a way that I cancel this factor n squared in the left-hand side of my equation. So this is to say, if I rescale time, or if I introduce a variable of time tau, which is rescaled as t to the n minus 2, which means that my alpha is equal to 2, then all of my scalings work correctly because I had a right-hand side which had this factor of n to the 2 globally. So I bring it on the left-hand side and I have this new factor of t over n squared, which I just define it as tau, and then I reproduce on the left-hand side the derivative with respect to tau. Okay, so this was just to give an idea of how one should do the things properly. So I think that what one has to remember is that you want to assume that you can rescale the arguments of your function and then take the limit n going to infinity, and in such a limit you recover a closed equation for a function which is just a function of your rescaled variables. Now the rescaling for the density is very natural, so the factor 1 over n is what we always expect because of extensivity of k, and in here you also have to rescale time in a way that you get a well-defined equation, and this is something that, if you think about it, it is quite natural because we are assuming that over a time scale dt, you have only one event which switch your k by plus or minus 1. But the equation that you're writing down is actually an equation for variations in phi that you can think of as k divided by a factor of n. So to have a very small variation of order 1 over n, you have to look at times which are much smaller than the ones of your original discrete process. So at least you understand why your tau has to be rescaled by a power which is negative in capital N. And the fact that this is equal to 2, well, in this case, it just comes out from the explicit expansion and your calculation. Okay, so anyway, this is just to give an idea of how one takes a continuous limit by doing expansions in terms of powers of 1 over n. And as you see, you get out a Fokker-Planck equation that now we are gonna interpret and solve for the stationary state. And this is a Fokker-Planck equation that you could guess a priori, remembering how one derives Fokker-Planck equation from the Langevin equation. So now let's keep this. I will rewrite this expression for the equation, and then we actually try to see how you could guess it without going through all of this lengthy expansion. And this is actually point 2 of the exercise. So this is the derivative in time. So the drift term, you have this d over d phi of epsilon 0, 1 minus 2 phi p of phi tau, and then you have the diffusion term. Which looks like this. Okay. Now let's forget about this calculation that I just did, and let's assume that I give you this Fokker-Planck equation and I ask you to justify why it looks like this, given what you know about the process in discrete space and in discrete time. So this is point 2. And the way you can justify it is by recalling something that I sketched very fast at the end of the last TD, but which you find, so recall the solution of TD3, where you have a derivation of Fokker-Planck equation from the Langevin equation. And the crucial point in the derivation is just to remember that you essentially need to compute two quantities, which are an average and a variance, that are what enter in here, of your incremental step in an interval dt. So these are the quantities that I defined last time as E1 and E2. This is if you have in mind an underlying Langevin equation, they looked like this. So you had an average of your incremental step in the interval dt, and that is what I call D1. And then you have the same thing, but with a square, which was E2. And now this is the transition probability coming from your underlying Langevin equation. And if you have these two moments, then your Fokker-Planck equation takes the general form. So your dp, in this case, it would be of x and t. In our case, x is equal to phi, but okay. Was what? So it was minus d over dx of your first moment, E1 of x, p of xt, and then you add the second derivative. And this is something you find if you do the derivation properly. And I also mentioned last time that, so this form is generic, whatever is the prescription for the noise that you take. What changes, and that will eventually give you different forms of your Langevin equation, of your Fokker-Planck equation, is the computation of this I1. So this quantity will be different whether you choose Ito versus Stratonovich, but this is not important in here. But this is just to connect with what we saw last time. So given this intuition that we know, what we want to do is essentially to recognize that what you have in here is an average increment, and that what you have in here is the average of the square increment. And therefore, with this argument, we can justify the form of our Fokker-Planck. So how can we do this? Well, we start from our discrete process in terms of k. And we use the fact that in the discrete setting, the probability that you end up in, so you can have only increments by 1 unit with a probability that was just given by our rates. Okay. And so now the analog of these averages will be averages over this now conditional transition probability. And the possible values that your increments can take in the discrete setting are always plus or minus 1. So this means that, so let me first compute what is the average increment delta k. So this is equal to delta k equals to plus 1 times the probability that delta k is equal to plus 1 minus delta k equals to minus 1 times the probability that delta k is equal to minus 1. And therefore, if you just plug this expression, you see that this is just dt times the rate of plus 1 plus the rate minus 1. Now we plug in our expression for the rate. And if you do the algebra, this you recover that this is, sorry, this is, yes, precisely given by this. and I forgot a minus. So this comes with a minus because it should be delta k equals to -1 times the corresponding probability. So the term which contains gamma cancels, and you just have to sum the terms which contains epsilon, and you get this. And if you do the variance in terms of k, in this case, this will be just the sum of the two transition rates. So instead of a minus, you would have a plus, and you find that this is equal to dt gamma phi 1 minus phi plus epsilon. So we are almost there. This looks almost like what we want for our Fokker-Planck, except one thing, meaning that we are now reasoning with respect to k, but the increment that we care about are actually with respect to phi. So we have to rescale everything by a factor of n. So let me do it up here. So what would be I1 of phi in my notation of before is what? Is the increment in k divided by n. So this is simply epsilon 1 minus 2 phi dt divided by n. Whereas I2 is just this. And so I have dt over n squared gamma phi 1 minus phi plus epsilon. And now again, you see that you have these factors of n which appear. And in order to have a well-defined process where you have both drift and diffusion, you have to kill these extra factors of n by rescaling both epsilon in here and rescaling the time. So this means that the time in which your Fokker-Planck dynamics will occur will be such that this is of order 1, and therefore you will define t over n squared to be a rescaled time variable. And if you do this, this will be of order n, and therefore you have to redefine epsilon to be some constant epsilon 0 divided by n. So you recover your rescaling of time from this shortcut, and once you do this, then this epsilon will disappear because it is of order 1 over n. So your drift will only contain this term, which is what you see in the Fokker-Planck equation up there. And sorry, your diffusion and your drift will contain epsilon 0 times 1 minus 2 phi, which is what you see up there. So this is a way that is a little bit shorter to avoid doing the lengthy expansion, or at least to justify why your Fokker-Planck equation takes that form. Okay, so are there questions here? That was the most, let's say, technical part. And if not, then what remains to do is to characterize the model is to try to, in principle, solve the full Fokker-Planck equation. So we are not able to do this, but we can look at the stationary state. Yes. Yes. Yes, I think that whenever you write, when you start from the master equation, you are doing some, so we're not starting from a Langevin. So the problem is not, let's say, defined from the start because we do not have to specify prescriptions for the noise, but we always assume independence in the little time interval. And so this will lead you to an Ito-like equation. And indeed, the Fokker-Planck equation that you get up there. So the question, sorry for those who are online, is we get a Fokker-Planck equation that is in the Ito formalism, if you remember. So why is it so? From where is it encoded from our derivation? And this is embedded in the fact that we are assuming somehow that the processes that occur in the event dt are independent, and so this corresponds to the Ito. But this is a good observation. So if you, what would be the form for a Stratonovich Fokker-Planck equation? So if you remember, you would just have a slightly more complicated structure in which you have one derivative, then one factors of g, which is now the square root of this, and then you have the derivative and then the square root times p. And this is nice because now we are going to solve for the stationary state, and we will find a solution that corresponds indeed to the Ito solution. And if you have a different form, if you use the Stratonovich, the form of the stationary state will change, so you can try to do this as an exercise. Okay, so let's now try to compute this stationary state, and then we conclude. There was maybe a comment before. Yes. So before or while I raise, just one comment on the form of the equation. So you see, you have the drift term and the noise term, and they somehow push you in different directions. So the drift term vanishes when phi is equal to 1/2. So 1/2 means that you have half population of type A and half population of type B. So the drift term is somehow pushing you towards 1/2. If you are away from 1/2, you have some kind of force that pushes you to reach 1/2. Whereas the noise term is pushing you away from 1/2 because the variance of the noise is maximal at 1/2. So the noise wants you, if you are sitting at 1/2, it tends to, with its random fluctuations, to push you away from the middle towards the extrema, where the noise is 0, which are phi equal to 1 or to 0, which means that all of the population is either in state A or in state B. So there is a competition between these two terms, and so we expect to see this competition also in the stationary state. And indeed, we will have a parameter alpha on which the stationary state depends, which is just the ratio of the two with a factor of 2. So let me define it properly. Yes. So depending on whether alpha is larger or smaller than 1, you will have different forms for your stationary solution. But let's compute them, and then we are done. So this was point 3. So what it means to compute the stationary distribution. So the stationary distribution does not depend on time. It satisfies the dp stationary. You have to set to 0 the left-hand side. So actually, whenever this is true, you have a stationary distribution which depends only on phi. And now if I set to 0 the left-hand side, let me look at the right-hand side. So the right-hand side contains many derivatives. And what I can do is, so the right-hand side, I can write it as a global derivative, maybe with a minus, of something that I can call a current. So what is my current? So here is 1 minus 2 phi times p minus 1/2 d over d phi of gamma phi 1 minus phi times p. So if I set the left-hand side to 0, then I'm saying that this quantity has to be equal to 0, which means that whatever is in parentheses, which just depends on phi, its derivative with respect to phi has to be equal to 0, so this quantity has to be equal to a constant. Okay? When I evaluate it at the stationary distribution. Because in that case, this derivative is 0. Now, what is this constant? Well, since this constant is, so you have the p in here, and you don't want a dependence on phi, so what you can argue is that you should actually choose this constant j to be itself equal to 0. And the reason is that if this was not the case, then you will, so you would get a distribution that is not normalizable. So what you want is that p when phi goes to, well, here we have a bounded intervals, but in general, if you think about unbounded distributions, you want to that p decays such that you are normalized. And in order for p to decay such that you're normalized, it must go to 0 when the argument goes to infinity. But if it has to be constant, that this means that p itself or whatever, or the combination of p and its derivative has to be equal to 0. So you can argue in general that because of normalization, you can set your current equal to 0. Or if you want, you just assume that this is 0 and you find a stationary solution that satisfies your equation and which, by definition, will be stationary. So let's assume that our current is 0. So this now gives a linear differential equation for our p that I rewrite and that we can solve in 3 steps. So we have E0, 1 minus 2 phi p stationary of phi minus 1/2. Now I have d over d phi gamma phi 1 minus phi p stationary of phi. This has to be equal to 0. And now we solve this equation in 3 steps. So the first step, or at least I find it easier to solve it in 3 steps. So the first step is to do some rescaling. So you see I have a linear equation, but here I have phi which appears everywhere. So let me define this as some p tilde of phi, so that I have the derivative of p tilde, which is easier to handle. So I introduce p tilde such that this is gamma phi 1 minus phi p stationary. And then I write the equation for p tilde. So I will have E0, 1 minus 2 phi. Then p stationary is p tilde of phi divided by gamma phi 1 minus phi. And on the right-hand side, I just have a factor of 1/2. So I bring the 2 up here. And I just have d over d phi of my p tilde of phi. Okay. And now once I did this rescaling, I can do something very easy, which always comes out from the structure of this equation, which is that I can integrate this equation with separation of variables. So in a nutshell, separation of variables, you've seen examples in the lecture already, means that I bring on the right-hand side all the terms which depend on p tilde, and I leave on the left-hand side all the terms which depend on phi. Or if you want that I rewrite this equation in differential form, so if you are sloppy, it means that you take this d phi and you bring it on the other side. But in differential form, you see that this is equal to 2 epsilon 0 over gamma 1 minus 2 phi, phi 1 minus phi times d phi. So everything you have on the right depends on phi, everything you have on the left depends on p tilde. And so now what you can do is to integrate both terms. So you integrate the right-hand side from some phi 0 to some phi, well, let me call it phi tilde, so that I integrate up to phi. And the left-hand side you integrate from the corresponding value of the distribution at phi 0 and the one at phi. Okay. And now these are integrals that you know how to do. So on the left-hand side, you have a logarithm because you have 1 over p. So you will get log of p tilde of phi divided by p tilde of phi 0. And on the right-hand side, we use exactly the same trick that I mentioned in the first exercise. So you have a quadratic expression in phi tilde in the denominator. I want to split it as we did with the x1, x2. And here it's easy. So this, you can write it, I think, as simply this. You see that this matches exactly. And then you can integrate. So these are just logarithms. So if you integrate, you have 2 epsilon 0 gamma. And then you have the log of phi over phi 0 minus, but then the minus is already inside the derivative. So this is the derivative of the log of 1 minus phi. So here I have a plus log of 1 minus phi divided by 1 minus phi 0. And then, well, phi 0 is arbitrary. So let me rewrite this as 2 epsilon 0 gamma. So this was the alpha that I introduced before. Then you have log of phi 1 minus phi divided by phi 0, 1 minus phi 0. And then I can exponentiate, right? So if I exponentiate, I get my p tilde. So p tilde of phi will be some constant which depends on this arbitrary phi 0, which I just call c. So eventually all of the constants, I will fix them by normalization. So I don't need to keep track of what is the constant at this stage. And then I have phi 1 minus phi to the power of 2 epsilon 0 over gamma. But now I have to remember that this is rescaled. So this was phi tilde. So from here, what is, I rescale back, if you want, phi stationary of phi is what? Is 1 over gamma, which is into my constant. So I have a new constant, c prime. And then I have a factor of 1 over phi 1 minus phi in the denominator. So this will be, I will write it like this, phi 1 minus phi to the 1 minus 2 epsilon 0 over gamma. So all of the constants which did not depend on phi, I encoded them in C prime. And the reason why I don't need to care about those is that I can fix the global constant now by simply normalizing my distribution. So this is step C, which is normalization. And this is a chance for me just to introduce one identity that maybe is useful to remember, which is a gamma function. But anyway, what I need is that the integral from 0 to 1 of my phi of my distribution is equal to 1, and this is C prime integral from 0 to 1 of 1 over, so actually now I will write it as phi 1 minus phi to the 2 epsilon over gamma minus 1 in d phi. Okay, so C will be the inverse of this integral. And the reason why I'm writing it explicitly is just to give you something that you know. So this is an integral that is well known in the literature. It is related to the so-called beta function, which in turn is related to the gamma function. So the gamma function is a function which is defined in terms of the following integral representation: t of x minus 1 e to the minus t. And the beta function, so anytime you see phi x 1 minus x integrated between 0 and 1, it is almost always related to this beta function in here, which is precisely this: t to the x minus 1, 1 minus t to the y minus 1 in dt. And this is related to the gamma function, so you can show these are identities. This is gamma of x, gamma of y divided by gamma of x plus y. So using this, you can compute the normalization. So you can find that C prime is nothing but gamma of 4 epsilon 0 over small gamma divided by gamma of 2 epsilon 0 over gamma. So typically, we don't care about the normalization here. I want to write it down because I want to take now a limit and discuss what happens when epsilon 0 goes to 0. Okay. So these are general identities. And what we also need is that when x goes to 0, your gamma function is divergent. So you have a divergence that you can compute explicitly. So you have an asymptotic expansion when x goes to 0, which tells you that you have a pole which goes like 1 over x, and then you have something of order 1. Okay, now we use this just to comment a little bit on the structure of the solution that we obtain, and with this we finish, I think, the exercise and the TD. So it's maybe 2 comments that are related to point to the final point. So the first one is that, as we mentioned, you have this competition between epsilon 0 and gamma, and you see that this emerges in this combination, in this ratio, in the distribution that you have. So you have alpha 2 epsilon 0 over gamma. And you have 2 situations for your stationary distribution. So this goes from 0 to 1. So if alpha is larger than 1, then your distribution is proportional to phi 1 minus phi. So let me rewrite it. So P stationary goes like phi 1 minus phi to the 1 minus alpha minus 1. So you see, if alpha is larger than 1, the exponent is positive. So you will have something which vanishes at 0 and 1, and which is symmetric with respect to 1/2 and has a maximum at 1/2. So you expect something like this, which means that if you think about your animals, half of those will likely go to the source A, half of those will likely go to the source B, and they will be more or less evenly distributed. But if alpha becomes smaller than 1, then your distribution changes, because now this product goes into the denominator, and so you have a divergence at 0 and at 1. So you're still symmetric, but well, I should use colors maybe. You have something which looks more like this for alpha smaller than 1. And so this is the regime where you tend to have a very opinionated population, if you want. So your population is either strongly in favor of the choice B, which correspond to phi equal to 0, or even strongly in favor of the choice A, which correspond to phi equal to 1. And this is because the term which corresponds to the noise, which pushes you toward this extrema, is winning with respect to the term which corresponds to the drift that was given by this spontaneous change of opinions of your population. And with all of the expressions that we derived, you can even ask what happens in the limit. So this is the second comment. You can now take the limit epsilon going to 0. And in this limit, so alpha is going to 0, and you get, so as you approach this limit, so should I do this? Yes, so with the expansion that I told you up there, what you find from the normalization constant is that when epsilon 0 is much smaller than 1, this is going like 1 over epsilon 0, I think. Sorry, this is going like epsilon 0. So you see from this expression, you have a coefficient in front which goes to 0 when you send epsilon 0 to 0. And you have an exponent which is going to 0. So you have a term which is 1 over phi 1 minus phi times something which is going to 0. So this means that as long as phi is different from 0 or 1, you are regular with this term. And so your distribution is going exactly to 0 in this limit, except at the points where phi is equal to 0 and phi is equal to 1, where you have a pole. And so your distribution is exploding. So in the limit, if you picture this, if you make epsilon 0 smaller and smaller, you start having distributions which become more and more flat towards 0, but then which explode at 0 or 1. So this means that your phi stationary in the limit epsilon going to 0 converges to a delta where all of your population is either in 0 or it is either in 1 with half and half probability. So if you average over time, you will find, or over realizations, you will find that in half of your realization, all of your population chooses A. In half of your realizations, all of your population chooses B. But they are somehow all agreeing, and there is not a well-defined stationary distribution as you would get for in the regime of parameters where alpha is non-zero. Okay, so this concludes, and maybe just the final comment to comment on the first exercise. So for this type of model, you can even compute when epsilon is different from 0. So this exercise 3. When epsilon is different from 0 but finite, you still have, let's say that alpha is smaller than 1, you still have this distribution which is very polarized, concentrating on 0 and 1. But in that case, in the dynamics, you can still have, let's say, it is in this case, if you start from 0 or from 1, you stick to 0 or to 1. These are absorbing states of your dynamics. In the case epsilon 0 is positive, you can still go from having all of the population concentrated in 0 to having all of that concentrating in 1. And you can compute what is the switching time between these two choices. And you find that this is of the order of 1/2 epsilon 0. So this we are not going to compute. But this is in a way a little bit similar to this jump calculation of the jump times that we did in the first exercise. And the interesting thing is that this depends only on epsilon 0, and it does not depend on gamma. So on the recruitment, on the discussion between your agents. So in that situation in which epsilon 0 is small, you really have that one of your ants or animals or people changes its mind, and then you trigger a full avalanche where everybody else follows, and you jump from this situation to this situation. So the dynamics is really abrupt, and this is related or similar to avalanches that occur in many other systems that are complex and with many agents. Okay, so I think that's enough. And the remaining exercise is, as I said, it's a little bit different. It goes back to statistics, but it's a nice way to see an application of Brownian motion. So if you have time, have a look at that. And there is the homework related to that, which is homework 8. And that's it. So next time we will do the final today, I think. So is there any question? Otherwise, I will stop.